Sorry.
Hello, guys. Welcome to this webinar. Nice to have you here today. So today we're going to talk about NURBS topology. Let me just turn off the audio in my control screen, my monitor. Okay. I see some people here in the live YouTube streaming. Hello. Hello, Giovanni, buongiorno. Okay, so nice to have you here, guys. I really appreciate your interest in my work. We are streaming on YouTube as well, so this is going to be probably the default way I'm going to spread my new material. So I strongly encourage you to subscribe to my channel. For those who are on YouTube, you just have to press the subscribe button. It's quite easy. And for those who are listening or watching this webinar on Zoom meeting, because they managed to register on time, you just have to surf the web and reach my YouTube channel and subscribe. Therefore, in that case, for example, you will also receive automatic notifications and about new events coming up. So as I was saying, today we're going to discuss NURBS topology. Of course, I think we are all Rhino users, so of course we are going to discuss NURBS topology in Rhino. So let me quickly introduce the reason why I am doing this webinar, besides the pleasure of sharing some knowledge with you all, is because I wrote this book, which is available on Amazon.com and on basically almost all the Amazons in the world. It's available in Italian, English, and Spanish, so you can find it in either one of these languages. Actually, for those who are in Mexico, you can directly contact me if you want a copy of this book in Spanish. I just have very few copies left. This is basically the main image. This was the excuse for writing this book. I don't know if you know the story, but if you own the book, you should know it. When I published this image online, I was asked to make a tutorial on this car, and I got quite pissed off because you can imagine that writing or streaming a tutorial about how to model this car would require maybe weeks, okay, to complete all the job, and that's why I wrote the book. So my approach is that not everything can be summarized in tutorials or webinars as this one. Webinars and tutorials are a good tool for those who already have an idea of what they want to do and what goal they want to achieve, and they are stuck with a very specific problem. But I do not recommend to rely only on tutorial and webinar if you want to deeply understand the concept and the topics that you are interested into. Okay, so this is my personal approach. And inside this book, there are basically many considerations on NURBS topology in order to, turn the average user into a professional user. So it's not a manual. This is a common mistake. It's a method. So there is not a complete discussion on all the comments that are available in Rhino and so on. It's just a method. You get fully understanding of NURBS topology, and you get the necessary background to understand how to deal with NURBS topology while working with Rhino and Rhino tools. And then there are some scenarios involving mainly the principal surface creation tools, but with a very deep analysis of how to optimize, for example, the workflow, how to be capable of deciding what workflow to undertake if you have to solve a specific problem. So once you know this method, you can simply take the straight path to the desired result without wasting time in a trial and error process. So you see, these are some images from the book. Maybe some of you already know this material. As you can see, for example, here you can recognize also that some digital fabrication content is also available in the book in the last part. I was dealing also with visualization problems. So visualization and fabrication are already inside the book as the last chapters, because they all depend also on topology, basically. So everything is connected inside this book. And what I'm doing right now is, well, proposing once again, because this was already in my catalog in the previous platform that I was using, a NURBS topology course, a full course, not like this webinar. This webinar can be considered like an intro to this online training, which is going to happen next weekend. If you want to achieve a professional level with Rhino, I strongly recommend that you become expert in NURBS topology, because many times, well, the success of a course to me is represented by the times that my students say, "Oh, if I knew this before." Okay, so, and this is actually what happens when I give this topology-based course. The last one was a couple of weeks ago with a private client. It was an advanced Rhino modeling course on jewelry design. So I got many times this kind of feedback, "Oh, if I knew this before." But anyway, this course is actually on offer because of this COVID-19 situation. So you will find it online, and you can participate. This is actually the last course that I've been recording. It ended just a few days ago on Thursday. It is called Kangaroo Reloaded, if you go on my website. And it mainly focuses on rigid bodies, tensegrity, and origami, because I excluded the first part, which is normally soft bodies like elastic shapes and textiles, because as you might know, they are the content of my first two webinars that I recorded a few weeks ago. So you can find the first part, like soft bodies, for free on my YouTube channel. And then if you want, now you can buy this video course on rigid bodies, tensegrity, and origami. Here is the 5x1 grasshopper bundle. You can see some of the screenshots from the classes that are available on YouTube, privately, of course. You can see that these are basically some of the classes. It's a total of, I think, 18 or 20, more or less 18, 20 video lessons for a total of more than 30 hours of material. So it's plenty of stuff. And as you might know, this is also a super deal that you might be interested in. These are the previous webinars that I have recorded. You don't see here the last one from yesterday, which was about loops in Grasshopper, but it's available online, so you can easily find it. And I invite you to subscribe to the channel in order to stay in touch and receive updates in real time. So today we are not going to discuss Grasshopper directly. We are mainly focusing on Rhino, but we will use Grasshopper in order to conduct some topological analysis of NURBS geometry in Rhino. Okay, so let's jump to Rhino interface. I'm going to share this screen. Okay, I think we see the same thing. Let me double check in the transmission. Yeah, I think it's coming. Yeah, okay, perfect. So I see my Rhino and Grasshopper interface. So you see this file, basically it's from an old study that I did about NURBS topology. It was during a course actually, but this study is from, I think, 2015 maybe. Yeah, I was recently, I was recently moving to Mexico. So yeah, it's already 5 years. Okay, but anyway, what this script does is basically conduct a deep analysis, deep topological analysis of this NURBS curve. I'm not going to discuss this in detail, uh, but what it does is basically calculates all the derivatives, and it was a basis for me for explaining the behavior of these NURBS curves in space and time also. We will not be discussing this in detail. If you want, it's in my book. But anyway, what I'm going to do, I'm going to start from this. Oh, by the way, you should eventually activate this in order to have access to all the information, which is here, by the way. So you have access to all this information about this NURBS curve, and you can see it misses this one, which is torsion. But anyway, and if you want, you can right away, you can simply tweak this thing, and you can see how this curve behaves in time with this definition. This is a very deep analysis. We are not going to discuss this today. And in general, maybe, unless you are not into, I don't know, automotive design or yacht design or something that requires a very precise aerodynamic control, then you might not be interested in this kind of deep analysis of a NURBS curve or a NURBS surface. But if you're in that kind of industry, well, you should eventually take into account that you should perform this kind of analysis. What we're going to do instead is concentrate on this series of points, which, by the way, are the points that are used to create this curve here. And of course, I can create this curve in Rhino. I mean, I can simply go and click some points around and activate the control points, and then eventually move some points up, move some points down, and get this kind of very similar result to the original curve. Okay, so this is exactly what I'm doing here in Grasshopper. I don't know if you are all into Grasshopper, but in my opinion, if you don't have a perfect topological understanding of NURBS surface, you will encounter many troubles and problems in Rhino. Actually, there is I can call him an ex-student of mine, which, by the way, was attending the Kangaroo course. So we left 2 days ago, but he has a problem with Kangaroo that depends on NURBS topology, and eventually he's not succeeding in creating the right Kangaroo definition because it lacks some NURBS topology knowledge. So what we are going to discuss here, which is simply an introduction, is fundamental, whatever type of work you are conducting, be it in Rhino or Grasshopper. So I strongly encourage you to familiarize with NURBS topology if you are working with Rhino or Grasshopper, or both of them. So let's concentrate a little on this curve. Now, you see that this analysis is better for me because it gives us access to two particular properties of this NURBS curve, which is something that you don't easily understand or get in Rhino, because if I go back to this curve, I only, in Rhino, you can only handle the geometric property of this curve, okay, not the topological one, at least not in a comprehensive way. So for example, if you want to, let's say, calculate the length of this curve, you easily have access to this length command, right? But if you want to deal with the parametric representation of this curve, which is way more important than the geometric representation. The only way that you can do it in a very, let's say, intuitive way is by handling or editing the control points. So control points are the main characteristics that allows to interact with this curve from a topological point of view. But when you switch, for example, when you start working with Grasshopper, something happens, and this is the main problem for many users. Something happens because Grasshopper is not based on the geometric aspect of NURBS objects. It's based on parametric representation. And we are talking about a different parametric meaning. So parametric means that basically all the design that you create is based on parameters, okay? But in this case, I'm talking about a different thing, a different thing, which is the parametric representation of geometry. So I don't know if you have fresh knowledge of mathematics, for example, or differential equations and so on. But anyway, you can think about this curve here as the graph of a function. Actually, this is the graph of a function, okay? And there is also an equation for this kind of geometry. But I'm not going to go deep into mathematics or NURBS mathematics, because you would simply shut the computer off and go away. But anyway, this is also on my book. So if you want to read it and have a deeper understanding, that you might read the book. But anyway, this is the graphic of an equation, okay? And you might know that, for example, when you have a mathematical function, and normally you have an independent variable and a dependent variable. So normally the explicit way of describing an equation is y equals something x, I don't know, with power of x eventually, and plus constants and so on. This is the explicit way of defining a function. But there is also a parametric way, where you basically describe the variation of x and y given a third parameter, which is normally indicated with the letter t. And it's interesting because normally t is associated with time. So what happens with this kind of shapes here is that there is one parameter, one additional parameter, which is called t, that normally goes from 0, which corresponds to the start point of the curve, and reaches a specific value when it gets to the end point. Now, when we work with Rhino, we have no idea of this specific value for the end point, okay? Unless we take this curve, go into the details, and see that this curve has, let's see, the geometry part, okay? This is an open NURBS curve. It starts in this point, it ends in this point. It has degree 3. It has 8 non-rational control points. We will discuss this in a while. And it has this thing here. Now, this thing here is exactly the other aspect of NURBS topology that you don't ever consider when you're working with Rhino. And it says that the domain ranges between 0 and 89.3052, okay? Now, remember this value here, 89.3, okay? So if I take this curve and analyze its length, it says 85.9, not 89.3. So the domain is not the length of this curve. It could be the length of this curve just in very, very, very particular situations, but normally the domain and the length are not coincident. So the domain depends on the topology, while the length is just a geometrical property, okay? So Grasshopper deals with the domain. And when you work with Grasshopper, now we can get rid of this curve. When we work with Grasshopper and create a standard NURBS curve, we have access to both values here, length and domain, okay? So if I take, for example, a panel, and I take another panel, you see that now we have this kind of representation. So this is another curve, of course, is not the previous one. So the length is shorter, 52.41. And there is this thing here, the domain. Now, this is called a normalized domain. So there is no actual variation of parameter t along the curve. But this is very important in Grasshopper because it affects many, many, many comments. Okay, so for example, let's say, for example, we have this point list and we have this point order. Okay, so let's take a look at this. So we have this curve flows according to this sequence of control points. Okay, um, and if you want to, for example, extract a point along this curve, there are two possibilities that you can use right now. One is the point on curve. The point on curve is extracting a geometric point along the curve. So you see that point on curve component, for example, if you right click on it, it says you can extract a start point, a quarter, third, mid, 2/3, 3/4, and end. Okay, so this is a geometrical evaluation. If I say 0.5, which is mid, I'm getting the geometrical midpoint of this curve. If I say 1/3, this is 1/3 of the length of the curve. So this allows to interact with the geometric representation of the curve. But if you want to parametrically extract a point along this curve, normally you would use the evaluate curve. And what happens with the evaluate curve? It asks for a curve, input curve, which is our NURBS curve here, and it asks for a parameter. Now, if I want to know what values to plug here, what range of values to plug here in order to cover all the extension of this line, in Grasshopper, you don't know it by default. You should take a look at this domain here. So it says 0 to 4. So if I say, for example, I want to consider a range between 0 and 1, you see that you have this point here that lies in the start point because parameter is set to 0. So time is 0 here. But when times reaches 1, we are not reaching the end point of the curve because the complete time span, if you want to call it like this, which is the domain, ranges between 0 and 4. So if I take a slider between 0 and 4, then in this case, I can flow all along the curve between the start point and the end point with value 4. Okay, but normally this is something that you don't want to do because this makes your whole process non-parametric. Because if I change something in this curve, the domain will change, and I should have to change this slider if I want to cover all the length of the line. Okay, so that's why, for example, in Grasshopper, you always, when you have this kind of parameter input, you reparameterize the curve. By reparameterizing the curve, you say, I don't care about the actual domain of this line. I want this domain to be converted instead of 0 to 4 or 0 to whatever it is. Please convert it in a new range, which is 0 to 1. So in this case, you can use a normalized slider, which is 0 to 1, and you have access to the whole length of the curve. So this reparameterization here has to deal with the curve domain. You are normalizing the domain of the curve. So you are converting this domain from any range, any actual range, to a new domain, which is between 0 and 1. Now, this looks very similar to the point on curve. But remember that the point on curve has a geometrical meaning, while the evaluate curve has a parametrical meaning. So if I set this to 0.5, for example, and I set this to mid, you see that these 2 points here are slightly different. Okay, so this depends on curve topology. Now, curve topology is defined by many aspects. Well, actually, mainly 3 aspects. Okay, but in Rhino, normally we only deal with one of them. Okay, we give for granted that the degree of the curves is 3, and we don't care about the knot vector. Okay, now we are not going to discuss the knot vector very deeply because it's quite complex to let's say discuss, and it should take lots of time. What I'm going to do eventually is instead make some examples here in Rhino, which is our goal today. So what I'm going to do, I'm going to work in the XY plane, and I'm not going to work in 3D. It's basically useless, or it doesn't add any feature, interesting or relevant feature. So what I'm going to do, I'm going to draw, for example, a couple of curves, like a control point curve. I leave degree to three. So I strongly recommend that you don't increase this value. Eventually, you might decrease it to 1 or 2 if you want to create some particular shapes. Like degree 1, you should get a polyline, and degree 2, you should get a piecewise curve, like the ones that you get from Illustrator, for example. So leave this to degree 3 if you want to obtain some organic shapes. And what I'm going to do, I'm going to activate the grid snap and draw some curves. Like, for example, one that has this set of control points, and then it becomes, let's say, smoother. And another one that has this set of control point here, and then it becomes way denser in the last part. Okay, so these are two degree 3 NURBS curves. Okay, their topology is completely different, but their geometry is absolutely identical. Okay, so this is a very interesting scenario. Okay, so what I'm going to do, I'm going to import here the first one, which is this one, and the second one here at the bottom. Okay, so I can also recognize in which order they are in Rhine. Okay, so this is the thing. If I evaluate these curves here, both of them, and I want to reparameterize them and use a normalized slider between 0 and 1. Of course, when I set time to 0, I'm at the start point of the two curves. If I set time to 1, I'm at the end point because I have reparameterized both of the curves. Okay, so they have both the same domain. But if I move along these curves, you see that the second curve, let's say the point moves faster in the first part of the curve, while on the first curve, the point is way slower than the second one. Okay, when I reach 0.5, this is the parametrical midpoint of this domain, 0 to 1, and this is the parametrical midpoint of the 0, 1 domain for the second curve. Okay, so you see that it is totally different topologically. Of course, if I increase this value, the second point becomes lower, while the first point accelerates because they have to reach the end point both at the same time, because it is time 1. Okay, so you see that topology in this case, and this is the interesting part, we can control topology in Rhino mainly by adjusting the control points. So here we have two different set of control points, and you see that where you have more control points, the curve is somehow slower, and where you have less control point and you have a more separation between them, the curve is faster. Now, why we should care about this? Okay, there are many considerations about this particular situation. One of them, for example, and this is the only one that I'm commenting, for example, is that also McNeil itself in its manual recommends that, for example, when you work with sweep 2 rails, it recommends that the 2 rails have the same topology, more or less. Okay, why? Because the speed of the rail is important in order to control how fast the two extremes of an eventual cross-section move or slide along the 2 rails. So this particular configuration might produce some twisting of the surface or some torsion along the sweep. Okay, so it's important to control the topology of the curves, even when you are working with surface creation, well, especially when you are working with surface creation comments. Okay, so for example, if I do something completely different, like create some curve like this with many, well, not like this, but with many control points in this area, and then eventually less control point here, okay, like this. And then I create another curve with few control points here and more control point in this end part. Okay, and then I create another curve with a few control point and then more control point and then few control point. I'm not taking into account the smoothness or aesthetics of this curve. I just need a different topology. So if I use this curve for a basic command like the loft, for example, and I try to loft these lines here, what I get if I don't simplify, well, this is an ambiguous term, but if I don't simplify the curve, I get this thing here. So you see that the topology of the surface coming out from these curves is totally irregular. The surface itself is a flat surface. So actually, there is no particular geometric consideration on this surface. If I convert it or turn into a shaded viewport and take a look at this without the isocurves, what I get here is a simple flat surface. So eventually I could also take this and extract the border, have access to these lines, and represent this with a simple surface from planar curves. Geometrically, these two things are perfectly identical. Okay, so there is absolutely no difference between the two from a geometrical point of view. But from a topological point of view, isocurves tell us that there is a totally different topology behind them. Now, we don't want to have this kind of topology in a surface. And this topology comes exactly from the topology of the cross sections. Okay, so you see that, for example, isocurves are denser in areas where you have more control points. This depends on the fact that control points are let's say, a visual control over another aspect of the NURBS curve, which are knots. Okay, so the knot vector in a NURBS curve is very important. We have no control over the knot vector directly in Rhino, which is not exactly correct, but take it for good. But anyway, we have no direct control over knot vector. What we can do is just place control point, the best we can. Okay, so in this case, for example, you see that having many control points here and here and here is determining this kind of wavy behavior for our isocurves. This is a very problematic topology because not because of the geometrical aspect of the surface, but because if you want to do some, let's say, further intervention on this surface, you have some problems. Because, for example, if I want to extract isocurves to produce cuts along this surface, you see that the isocurves follow the actual shape of the visible isocurves. Not in the V direction. If I switch to this, you see it is only a, let's say, morphing between the first section, the second section, and the third section, okay? But in the longitudinal direction, which is the U direction, you have this kind of weird behavior for your isocurve. So if you want to create, for example, some holes inside the surface, this topology is problematic because it is extremely irregular. So what you might want to do eventually, you might want to rebuild these lines because rebuilding is one topological operation that allows to make two things. First one, you can simplify in Rhino terms, you can simplify the topology. And the second effect is you basically obtain a more regular topology. So for example, if I rebuild using the standard rebuild command, not the rebuild curve non-uniform, but the rebuild curve, and then I rebuild this one, you see that you can decide, for example, well, I would leave the degree untouched, and you can decide how many control points you want to have. Now, all that we are saying can be analyzed inside this little dialog window here. So amount of control point, 12 instead of 13. And degree is 3. And then there is another parameter, which is not, let's say, editable, which is this span count. This span count is a representation of the knot vector. So it is saying basically that if you have 13 control points, you have 10 spans. 10 spans means that your curve is divided into 10 segments. Okay, so you have 11 knots. Each knot corresponds to one endpoint of each span. So 10 spans means that you have 11 knots. One knot corresponds to the start point, one knot corresponds to the end point. And you see that there is no possibility here to edit this value here. You only see that if you lower the control point values from 13 to 12, you get a 9 spans instead of 10. So decreasing the number of control points by 1 is also decreasing the number of spans by 1, which means that you are also decreasing the number of knots by 1. Okay? So this is the control that you can have inside, for example, the rebuild command as regards the knots distribution. Okay? And there is another interesting parameter, which is more from a geometrical point of view, which is the maximum deviation. So this is a geometrical parameter that allows you to understand if the rebuild is producing some dramatic effect, something that you eventually might not want to take into account or consider. For example, if I am working with millimeters right now, and I'm getting a maximum deviation of 0.54 millimeters in this point here, this can be acceptable or not from the designer, okay? But if this was, for example, the path of a highway, okay? And so we are working in, well, let's say kilometers, right? So one little square is 1 kilometer. And this means that in this point, we are having a deviation of 540 meters. So this is something that affects the design. And eventually, well, actually, is the difference between a project that can be built and the project that cannot be built. Okay, so it depends on the scale that we are considering and what margin we have about the tolerance, basically. So in this case, this is a geometrical consideration. Okay, but you see that you have a full let's say, understanding of what happens in this curve while you are rebuilding it, both from the topological point of view and the geometrical point of view. So for example, if I cannot accept this kind of deviation, like 0.54, and I want to reduce this maximum deviation, normally I would increase the amount of control point, okay? So you see that if you increase this, you also increase the number of spans and you decrease the maximum deviation. Okay, and this is normal because more control points means you have more control over the curve. There are some basic rules for understanding how control points affect the shape of a curve, not only in the initial part and the end part, but also in the internal segments. We are not going to discuss this, by the way, in this webinar. But you see that if I increase the number of control points quite much, then you have this kind of very, very small maximum deviation. Okay, and eventually this is acceptable for any designer or at any scale, basically. What happens if I set this to 13? You see that even if I consider the same amount of control points, same degree, I have the same amount of spans, okay? I still have a geometrical deformation represented by this maximum deviation. So in this point, I get this deformation. The maximum deviation normally occurs in areas where curvature is very high, okay? And the reason why this happens, and I'm going to not delete the input and leave the two curves, is this. This is the rebuilt curve, okay? And this is the original curve. Let's take a look at them on the top view and activate the control points. So you see that rebuild not only can change the amount of control points and the degree of the curve, and therefore also the knot vector, but it redistributes the control point along the curve. So you see that in this rebuilt curve, the distribution of control point is basically more even. Okay, so you see that besides the first two and last two control points, all the rest of the control points are evenly distributed along the line. While in our original configuration, original topology, we had more control point concentrated here and less control point in the second part. So less control point, you see there is a smoother aspect for your curve, and more control point, you can have a more wavy aspect because there is more local control. This phenomenon here is called local deformability of a curve. So in order to have local deformability, you must have more control point. This is important because if you rebuild the curves and you can reorganize the structure of control points, it also means that you are reorganizing the knot vector and the knots along this line. Now, one thing that people doesn't know is that isocurves are actually not lines. Okay, so if you reorganize the control point, you are reorganizing the knots and you are reorganizing the isocurves. So for example, in this case, I would do something like this in order to give more regularity to this loft, in order to make make it easier for me to do some intervention on this surface. I would do something like this. I would use a rebuild command on this section, for example, here, in order to understand what deformation I get when I use a certain amount of control points. I don't want to change the degree, of course. So the only thing that I can change here is the amount of control points. And I want to get an acceptable maximum deviation. So we saw, for example, that if I increase this to 30, I already have an acceptable maximum deviation. This means that the shape of the resulting curve is more or less equal to the shape of the original curve. So I delete the input eventually, and I take the new section as the section that I'm going to use for the loft. So if you do this analytically, like I'm doing, you should rebuild this one and this one, okay? But I also see that this curve is smoother than this one. And this one as well is smoother than this one. So I suppose that 30 control points are enough also for this one and this one. So instead of rebuilding this curve here, I would use this 3 curve for a loft. And eventually I will rebuild these lines with 30 control points because I know that the resulting maximum deviation is acceptable for me, okay? I did the rebuild curve initially for just one section, which is the more geometrically more complex one, because I wanted to make sure that the amount of control points I was about to decide wouldn't give me too much deformation, okay? So once I know this, I can use the same amount inside the loft options. And I had to double check because as you can see here inside, you don't have any information about the maximum deviation, okay? What we are doing here is basically rebuild all the cross sections at once with 30 control points. We are reorganizing the knot vector for all the 3 curves. And this means that the isocurves, which are knot lines, which corresponds to the knots of these lines here, are more regular along this surface. So if I do this, I get a surface which is more or less identical to this one and this one, besides the maximum deviation that we got on this line and on this line. The inner line doesn't affect anything in this moment because the surface is flat. If this wasn't flat, we should also be considering the deformation that occurs along this intermediate cross section, okay? But in this case, we have basically an identical geometrical aspect between these 3 surfaces, but the topology is totally different. So this is more suitable for producing some kind of controlled result when it comes to additional interventions. For example, if I try to extract isocurve on this one, I have an extremely regular set of isocurves that I can use, for example, to create something like, I don't know, cuts along this surface, like this. So if I use this to create trimmings, like here, you see that at least in the longitudinal direction, I have regularized the surface so I can get this kind of nice holes along this surface. Okay. One last consideration that I would like to do about controlling NURBS topology is this. You see that my surfaces are, well, either whitish or orange. Okay. This is because my Rhino is set to display the negative face of a NURBS surface. This is important to control. It's another important topological consideration on NURBS surfaces because you don't want to see the negative face of a surface unless you really want to. Okay, so normally you want to see always the positive orientation, the positive face of a NURBS surface. How do you do this? You go, first of all, you use a shaded viewport like I'm doing right now. Then you go here in perspective, right click, go into display options, and the Rhino options window pops up in a few seconds. Here it is. And it pops up directly in the view settings, shaded settings. So here you have all the settings for your shaded viewport, and you simply tweak the backface settings. I normally and set this to single color for all back faces. So each time you see this color, you are seeing a back face of a surface. And I do recommend that you never use a single back face color, like, for example, I don't know, the primary colors, like the ones between white and dark green. Because normally these colors are used by any Rhino users as standard or default layer colors, for example, or object colors. So use some of these colors that are here at half this list of colors, because they are quite uncommon, okay? So that when you see that color, you are sure that you are not seeing a display color of any object, you are seeing a back face, okay? So how can we recover from this weird situation? Well, you might know that as for surfaces, you can use the analyze direction command, okay? So many users simply use the right click on this command, which is flip direction. I don't recommend you do this because let me switch to wireframe. Okay, we know that this surface has some orientation problem. Okay, so let me move it like here. We know that it is facing downward. So if I select this, instead of flipping it, right click, I analyze the direction. So left click. Now, what we see here is the actual parametric coordinate system of this surface, the famous UVW coordinate system. And you see that the white arrow, which corresponds to the W, which is the positive normal direction for this surface, is pointing downward. This is what makes this surface look downward. So that's why we see orange from on the top side. Now, if I go and place myself on the tip of the white arrow, so I am actually looking at the surface from its positive normal direction, okay? I must understand how the U and V axes are oriented. And you see that red is pointing right, which is U axis, and V, which is green, is pointing up. So you see that here we can recognize the default orientation of any coordinate system. So X pointing right, Y pointing up, and the positive Z is the positive vertical direction, okay? So the internal coordinate system of a surface should correspond to this orientation for the three axes. And I see that if I go here at the bottom, I see this kind of orientation, because the white arrow is pointing vertically up, and then there is a red arrow to the right, and the green arrow is pointing up on the same plane. So this is a correct representation of the internal coordinate system UVW, which is, by the way, the parametrical coordinate system of the surface. What happens if I just flip here? If I just flip, what I'm flipping is the white arrow. Okay, I'm not flipping the internal coordinate system. I'm flipping just the normal direction, which, by the way, in this moment would be enough to obtain the white face of this surface pointing up. But this, allow me to say it, screws things up more than before, because we don't have a correct internal coordinate system. Because you see that the white arrow is pointing upward, the red arrow is pointing to the right, but the green arrow is going down instead of up. So in this case, I not only have to flip the white arrow, I also have to reverse the V, which is the green arrow. So I have also to V reverse, and now we have the correct coordinate system, parametric coordinate system, okay? So try to avoid flipping surfaces unless there is no particular meaning and you don't want to do any additional operation on that surface. In that case, you might want to just flip the surface and who cares, okay? But if you want to work with that surface, try avoid flipping and analyze the surface and go back to a standard axis orientation like this one. X to the right, Y to the top, and Z or white arrow pointing normal, positive normal position orientation, which is upward, okay? So once you see this, you just hit enter, and that's it. You have the correct orientation for your surface. Let's go back to the shaded viewport, and here you see that everything goes back to normal. But it's not just like flipping the surface, okay? So it's important to do this because this, for example, just so that you know, affects important comments like, I don't know, the UV curve creation application, and also the flowing on the surfaces and so on. So it's all these comments depends on the topology of the surface. Okay, so pay attention to these details when you work with surfaces. In order to complete, for example, and go back to our topological analysis of curves, you might want to use Grasshopper because it gives you many informations about topology. That's why I have this script here on top. For example, I would go back to not these two simple lines that I'm going to internalize and internalize. So if you want, eventually I can share this definition with you in the description of the video later on when it will be published on my channel. And you will be able to play around with this and see a more deep analysis of geometrical of NURBS topology for this curve. But I'm going to so I'm going to internalizing this and this. Any comments? Yes, of course, because when you import a surface in Grasshopper, and the topology is already set in Rhino, so everything depends on the topology of the object that you are importing in Grasshopper. Grasshopper by itself doesn't reorganize the topology of the objects. Okay, so if you have an incorrect topology in Rhino and you import it in Grasshopper, then all the comments that you will use on that surface will respond to the actual surface topology as well as curves. Okay, so for example, I'm not doing this with a surface because it requires some times. But if I take, for example, a curve like this, and I draw a curve here in Rhino, what I'm doing, I'm simply drawing a curve, one bottom up and one top bottom. Okay, so I set this one and this one. Okay, so if I, for example, take the control points of these two, that could also be exactly identical, of course, and I analyze, for example, the point list of these and point list of these, and set this to a higher value so they will be visible eventually. And let me hide the points. So you see that here we have points from 0 to 6, and here we have the points from 6 to 0. So also the point order is totally different. So you see that this goes from top to bottom, and this from bottom to top and top to bottom. So the curve orientation is different. Okay, so if I, for example, use them for, I don't know, an offset, I don't know, let's see if it works. You see that one curve is being offsetted to the right and the other one to the left. So it depends on curve orientation. And orientation depends on the series of control points and not vector. So it's very important to learn topology, because if you don't learn topology, you will have some undesired behavior both in Rhino and in Grasshopper. Okay, but anyway, this is a very stupid example, but you see that it is already showing us that if you have something weird happening in Rhino, this will be reflected in Grasshopper somehow. And so people start to find the solution on the fly. Josué, te voy a contestar en un ratito, ¿sí? Perdón. Josué is asking for the difference between using control point curve and interpolate curve. Okay, so average user, when something like this happens, says, okay, so maybe I should flip the curve, one of them, instead of using the original one and do something like this. Oh yeah, it works, and that's it. Okay, but eventually, if you know how things work, this is, from my point of view, is a waste of time. And if you don't understand what is causing this problem here, you will find yourself every time adding flip curves, flip surfaces, and so on. Now, with flip curve, this is not a problem. But if you try to use flip surface is a command in Grasshopper that is most likely to fail instead of giving you the right result. Okay, it's more problematic to flip a surface with respect to flipping a curve, and this is something that we can easily understand, because if we analyze a curve, we only have one direction, okay, which is this one. If we analyze these two curves, we only have access to these two directions, and we see it immediately. But flipping a surface, we saw that it's a complex topological operation. It's not just like flipping the W direction. You also have to make U and V, let's say, according to the standard representation of a coordinate system. Okay, so flipping a surface is not a simple operation. You don't just flip a surface. You flip and adjust the whole orientation of the U, V, and W axis. That's why normally it fails in Grasshopper. And that's why, for example, I myself try not to use the flip surface. If I find myself struggling with a flip surface, I prefer to go back to the previous part of the definition or to Rhino geometry and organize it or adjust it in order to avoid the flip surface, because this is an error that I was doing in the first part of the definition or in the 3D model that I was doing in Rhino. Okay. So see, topology is behind most of the time wasted inside Grasshopper and also in Rhino. Okay. As regards the that you will rather reorganize the point order inside the curve list instead of using flip curve. No, flip curve is something that works. Okay, so if you are in the middle of the definition and you see that there is an opposite direction for one curve, then you might want to flip it instead of going back and reorganizing everything. Okay, but normally I seldom flip curves, especially if I am working with a geometry that I was controlling, like in this case in Rhino, because I know about orientation and I don't use curves with different orientations. Okay, if I know that this is important in the rest of the workflow. Okay, but this is something that also affects, I don't know, loft commands and all the surface creation commands depends also on curves direction. Okay, so it's very important to understand also this feature of curves. Curves are oriented lines. Okay, and if you have oriented geometry, this orientation will affect all the operations that you are going to perform on that. As regards the you're welcome. As regards the difference between control point curve and interpolate curve, well, I would resume it like this. Every time you read the word interpolation in Rhino or Grasshopper, run away from it. Okay. So on the other hand, you have control. So control point is something that allows a better control over geometry. Okay. So I would quickly summarize this with a stupid example that I do every time in my courses. So let's say that you want to you have this I don't know how to call it, this boundary in general. Okay. And you want to draw an organic shape, always staying inside this area. You don't want your curve to basically go out from this outer boundary, okay? And you are going to use either control point curve or interpolate points. Now, of course, if you work with interpolate points and your shape is simply going to be something like this, which is in the inner part of your area, there is no problem, okay? So you don't need a specific control. But if you want to occupy this boundary here, this area, at its most, so you want to touch the boundary from now and then, and you try to do this with an interpolate point, an interpolate curve, what happens is this. You can have a regular part here, and then suddenly you want to touch the midpoint, for example. If you do this, for example, the only way that you can touch the border with an interpolate curve is that you place one point on the border itself. So you need to place the point here. But the shape of the curve depends on where you place the next point. So you see that if I place it here, the previous segment keeps dancing around And so the curve might go out from your boundary. Also, you might notice that even by placing this next point here, I'm still affecting this segment here. What I'm placing right now is basically the knots of my curve, okay? And as you can see, it's very difficult to control the shape of the curve by placing the knots, because knots are passage point for your curve, but you have no control over them in Rhino, because you have control by using the control points. What happens, I am simplifying, right? But in order for a better understanding of the difference between these two commands, there are things that you can do with control point curve that allow to not overcome the boundary, for example. Of course, if you want to stay inside from this region, there is no problem. But if I want to touch the border without going out of this rectangle, I would simply place 3 control points here, and I'm sure that I am tangent to this border and I'm not going through the lines. Okay? So each time I want to touch the border, I just place 1, 2, and 3 control points, and you see that the curve doesn't come out of the border. Okay? So I have more control with control point curve. Um, yeah, and the other aspect is this one, because many people, especially those that are into product design, industrial design, or jewelry design, and so on, they, which is something that I do recommend, they first sketch on paper, and then want to, let's say, put this sketch in vectors in Rhino. Okay, so say you have an image and you want to trace that image, basically. In that case, you might want to use the interpolate curve, because you simply click on passage point and you can trace the outline of your sketch easily. The problem is that if you want to adjust things later, you have a distribution of control points that basically becomes useless, okay? So I do recommend that you eventually get familiar with the way the control point works. For example, if I have, let's say that I have an original line from the sketch, which is this one, and I want to trace this with another line. Okay, so this is the pencil sketch that we are seeing. Eventually, I'm going to lock it. Okay, so it becomes gray. And I want to trace another line. I won't use this. I prefer to use this because this gives me access to a better control later. So for example, if I see that this line, for example, starts from here, and I need to place other control point, I don't place control points on the path, because I know that if I do this, my curve will lie inside the original curve. Okay, so there is this kind of deviation. But once I know how it works, and I'm expert enough, I tend to place the control point in the outer part. You see, because when I bend the next point, you see that I go closer to the original line. Okay, so once you are expert enough, you can start placing control points, and this naturally leads to a better position of control points. For example, you see that I need these 3 control points here are giving me control over this curvature. Now this part is smoother, so eventually here I need less control point. This part has more curvature, so I will place more control point here. And then this part is smoother, and another time we have more curvature, more control points, smoothness like this, and eventually the end point. Now, you see that this curve doesn't correspond to the original one, but its control point have a structure that allows better control over how much precise I want to be when tracing this curve. This is something that you cannot do when you are working with a interpolated curve. Okay, so I do recommend that you take into account switching your workflow from interpolation to control. Okay, because this is the best thing that you can do in order to have better control over your geometry. And you can see that you get an aspect that reflects more or less precisely the original line. Okay, so work with control point curves instead of interpolated curve, because it's the best way you can control geometry. And also you can do further intervention on your geometry, because if you work with interpolated curve, you place the passage points, but then, for example, let's do like this. I'm going to draw a sequence of points like this. and I'm going to draw an interpolated curve, like between these points here. You see that the curve starts dancing around, and that's it. If you select this and take a look at the control point lie in position that have nothing to do with the knots. So you have a structure of control points that doesn't correspond to this point here. Okay, I'm going to display them as red. And here are our control points that have no evident relation with the knots. Okay, so it's difficult to adjust this geometry based on the actual structure of control points, because we were not controlling the position of the control points. Okay, so try and work with the control point curves, because it's the best thing that you can do. Could you convert interpolated curves to control point? There is no need to convert interpolated curves to control point curve. They are already control point curve, but you are not creating them by placing the control point. You are creating them by placing the knots. Okay, so that's the point. Even when you create an interpolated curve, okay, like this, you are always creating a control point curve. You have no longer access to those points unless you do some edit points, okay? But you have control over control points, which is the default in Rhino. And control points are more useful than knot points or passage points, okay? In the end, what I showed, what I just, well, I deleted the rectangle with the freeform curve inside, but I was using a control point curve to determine, for example, the passage through a specific point, which is something that it's natural with an interpolated point curve, and you must know how to do it with a control point curve. So once again, you must know how to deal with topology if you want to create some organic shape with control. You're welcome. Let me double check if there is something on YouTube. Wow, okay, sorry guys, I was not paying attention to the YouTube. Okay, oh, okay. Let me go through this because I see some nice questions. Ariel, thank you for the commercial. I bought the bundle, I really recommend it. Okay. Can a straight curve have torsion vector? Well, actually, yes, it can, but it's very difficult that you have access to this kind of information in Rhino, but you can do this in Grasshopper. So yes. Knot vectors are just defining when, in which moment along the path of a curve, you pass from a span to the next one. Okay, so let's make it simple. So knot vector, for example, does something like this. You see that in this case, I'm creating a control point curve, very important, degree 3 control point curve. And what happens is that if I take, for example, the first control point and move it, you see that I am deforming the curve, but only down to a point which is more or less in this region here. So if I move this point, you see that the curve deforms, but only in the first segment, okay? The moment this deformation stops, like here, is the first knot, the first internal knot, okay? So you see it's invisible, actually, but you know that it is there. What happens with the knot vector? The knot vector defines the position of this point according to the position of the first 4 control points. Okay, so for example, you see that we have this sequence of control point. The first point is deforming the first segment of the curve. Okay, only the first segment. The second control point is deforming both the first and the second segment, but not the third one, which starts from here. Okay, this is something that's determined by the knot vector. Then the third control point is deforming the first segment, the second segment, and the third one. The fourth control point is deforming the first, second, third, and fourth segments. When you reach to the fourth control point and you switch to the fifth one, this one no longer produces any deformation in the first segment. That remains untouched, as you can see. So once again, topology, guys, if you know how to deal with topology, you can decide exactly what's the shape of the curve, what part of the curve is deformable and not deformable, and so on. So this that I just showed is the effect of the knot vector, okay? Which, by the way, in Rhino, the best way to control this property is via the control points. But you have to know all the relationship that occur between knot vector, control points, and degree, okay? This is starting to be quite complex, by the way. I'm not going to further discuss because it's really something that requires lot of discussion. Let me go back to YouTube. What is tolerance and how tolerance affects a curve and surface? Well, actually, this is something that is very important in general, not only in the parametric workflow in Grasshopper, but also in standard 3D modeling in Rhino. So you know that when you set the units, you also have this setting with this absolute tolerance, okay? Now, normally I used to draw in Rhino for jewelry. So you see that I have a very small value here for absolute tolerance, and I'm working in millimeters. So this is my standard basically. But this is important because people normally doesn't consider this thing here, the templates. This is very important because before starting to work, I do recommend that you choose the right template because it's a perfect balance between units and tolerance. So if you are, for example, into architectural design, I would recommend that you work with large objects meters, not centimeters, because meters allow a better interoperability with other softwares. Okay, so I would recommend that you work with meters. Many architects tend to work with centimeters. Eventually, if you are into interior design, well, in that case, you might want to work with centimeters. But in that case, you might have some problem when, I don't know, exporting to some beam platform, okay? But I'd recommend meters and large objects because you want an absolute tolerance that goes down to 1 centimeter. If you are drawing, for example, a building, you don't need to control measures down to 1 millimeter. Okay, if you need to, you can decide to work with small object meters because it has a tolerance of 0.001 meter, which is 1 millimeter. Okay, so once you select the right template, you have your tolerance set by default here. You can change it, of course. You can go here and change this value, but I do not recommend you do this. Okay, so what happens when Rhino is set to work in millimeters and with this kind of absolute tolerance? Rhino cannot see any detail which is smaller than this value here. So this is basically 1 micron, okay? So if I produce some change or I have some geometrical relationship between 2 geometries, which is smaller than 1 micron, then in that case, Rhino will not detect that separation, okay? So for example, when you have some kind of complex relationship, like, I don't know, I'm going to quickly create a deformation here in order to have a double curvature surface like this one, okay? And then I'm going to do something weird, which is drawing a line on this surface, okay? Yeah, like this. So does this line lie on this surface? Yes, but with a tolerance of 0.001 millimeters. So you never get absolute precision, okay? You get the precision you can accept, basically. So yes, it's important because if this curve lies on this surface with a tolerance of 0.001, because it was drawn using that tolerance, this means that you can also perform some kind of operation like, I don't know, let me draw another one like this. Then you can use, for example, these 2 curves in order to cut this part of the surface. Why? Because the curves lie on the surface with that tolerance, and that tolerance that we have been using is the same tolerance that Rhino needs in order to perform these kind of operations. Okay, so yeah, tolerance is absolutely important, and I recommend that you never touch the absolute tolerance value unless you know exactly what you are doing. What happens with a loft with different knots between the lines? How Rhino operates to make this geometry and how this affects? Well, yeah, Cesar, this is really, really too much. But I would really like to discuss this with you. But if you want, you can register to the course, because this is something that we are going to discuss in detail. And also, well, actually, surface by surface. So that's very important. Okay, Giovanni is asking what's the best way for switching between an irregular surface to a regular quad mesh in Grasshopper. Quickly, because this is another webinar, by the way, quickly, if you have an irregular topology like this one, NURBS topology doesn't affect mesh creation, okay? So the mesh creation depends on other parameters. So if you have a weird NURBS topology, this doesn't mean that you will have a weird mesh topology, not necessarily, okay? In this case, for example, if you use a mesh surface command, like this one, let me hide this, you see that the topology of this mesh is being obtained directly by the isocurves or by the knots orientation, okay? But eventually you can also regularize this topology, this topology basically, because in this case, in this particular case, in order to get a regular quad surface, what I would do, I would eventually rebuild the surface. Okay, so in order to have a better mesh topology. But in general, mesh topology is basically independent from NURBS topology. So for example, let's take a look at this. Okay, so I'm going to untrim this like this. Let's go back to the original surface. And I want to extract a mesh from this NURBS object. Okay, and so I'm getting this. Okay. You see that the topology of this mesh, yeah, it basically as regards the orientation of in general, yes, it depends on the NURBS topology, but the object that you create here can also be topologically extremely different from the NURBS one. So, for example, if I go into detailed control and simply refine this, I have a completely different topology for the mesh, which depends not from the topological distribution of lines. It depends, for example, from another geometrical aspect, which is curvature. Okay, so it depends on the result that you want to achieve. But in general, if you have an extremely irregular surface, like in this case, I would rebuild the surface, or as I did here, create the same surface with a different approach, which is rebuilding the cross sections, like I did here. Eventually work with this one because it is also flipped already. And so import this version here and have access to an extremely regular mesh like this one, okay? So the best thing that you might want to do is, it depends on the command that you are using for creating that surface, but I would eventually either rebuild the curves or rebuild the surface once it was created. Rebuilding the surface, it's something that has a more dramatic effect, especially when you're working with surfaces which are not flat like this one. If you rebuild this surface, the things that are more affected by the rebuild process are the curved edges. Okay, but if you have a double curvature surface and you rebuild it, then in that case you are changing also the curvature of the surface. Okay, so if I choose to work with the same amount of control points, you see that I am getting this kind of critical areas here where my surface is no longer reaching the same height. And you have a maximum deviation, which is starting to be important. So in general, I do prefer to adjust the topology first and then make some mesh conversion. But it depends on many factors, Giovanni. So it depends on the topology of the initial curve, the topology of the surface you are getting, the orientation of the surface also, you see that affects the orientation of the mesh. So there are many considerations that you might want to do. The flip contour in grass doesn't work properly for the whole grass definition. It's better to analyze the surface before going. Yes, I do recommend to control the topology of the original object, okay? Instead of doing some editing on the fly, Alessio, absolutely. Interpolate lets you define knot points and creates control points automatically. Yes, and NURBS lets you define control points and create knots automatically. Yes, more or less, yes. What if you need a corner control point? This will resolve the 3-point need. Yeah, in that case, you should know that a corner control point is actually a knot with full multiplicity. So, um, Javier, in that case, you might really want to know something more about topology and knot vectors, and in order to understand how they affect the geometry of the curve that you are creating. Yeah. So it is once again, it started to be a very, very detailed explanation. How do you find where control points should be located? Why interpreter will give useless control point? It gives useless control points because normally the amount of control points you need to perfectly control the shape of a curve is not the amount of control point you get from an interpolated curve. So which leads me to the first question: how do you find where control points should be located? By knowing what are the rules for placing control points along the path of a curve in order to get the desired effects. Once again, you should investigate more the topology, the NURBS topology part. Or read my book, or subscribe to, or register to the course that we are giving next week. Interpolate is a simple n-1 level division when you need an n-level ordered polynomial curve. Well, oh, sorry for the lag. Oh, yeah, if you want to go into n-1, I think you refer to the fact that there is a relationship between the number of control points and the number of knots in the vector. Yes, yes, it's like that. So if you know this, you might also know how to adjust the control point in order to get a corner point. What about tolerance for product design with limiter detail? Oh, I think, Alessio, this is something that I already said. So basically, the main problem that you get about tolerance for product design with manipulative details happen when you perform some kind of operations like projections, or eventually when you rebuild curves in order to have access to a better or more regular topology. In that case, consider that every time you do perform a rebuild, for example, you are deforming the curve also at a very fine detail level, and you are basically screwing the tolerance up. So in that case, you might want to double check that the resulting geometry still works in the inside the tolerance that you have in your document. That's the main aspect about controlling tolerance for product design. Is there any recommended method to convert weird surface to more regular? There are several methods. If you work, for example, with Grasshopper, there are also plugins that allow regularizing the topology, for example, of a mesh. But I think this is the same questions from before. So basically, I would eventually consider rebuilding the surface or rebuilding the construction curves of the surface. Thank you. Oh, you're welcome. Yeah, you are the. Yeah, this is being recorded, and I'm going to publish it later on today. So let me see if there is some other question. Could you show some slides about the NURBS course? How much will it be Rhino and how much Grasshopper? 50-50? No, it will be, I would say 80-20. 80 Rhino, 20 Grasshopper. Topology is something that that affects first Rhino and then Grasshopper. So it would be 80-20. What happens if you project the curve on the surface? Would it be more precise? No, it would be as precise as the absolute tolerance. Okay, so if you project, the projection is also made using the document tolerance. Okay, so there is absolute, well, the only difference is in the method you use for creating the curve on the surface. So either I was drawing directly on the surface, which gives me control over, eventually a little control over the shape of the curve along the surface. But if you want to project it, you have control more on the planar aspect of the curve, and then projection deforms the curve according to the surface, but the final curve will always lie on the surface with the document tolerance, the document absolute tolerance. Okay, so it's not more precise. Okay, so I think that's pretty it, guys. I see no further questions. So yeah, that's it for this webinar. I hope you enjoyed it. It was a little more technical than the previous ones, because when it comes to NURBS topology, two things happen. I get excited, like the nerd that I am, and also I think that this is the very basics for working with Rhino and Grasshopper. So I really think that you should go deeper in this subject, because if you handle topology properly, then you will have access to whatever secret in Rhino and Grasshopper. Thank you, Javier. You were not thinking topologically, yeah, yeah. Sorry for you if you are starting to think topologically. I'm so sorry. Okay, guys, thank you very much. Thank you very much. So see you soon. This was the last webinar for this series. I'm going back to class on Monday, and I will upload new stuff and organize new webinars in the next future. So stay tuned. Next weekend there will be the new course on NURBS topology, mastering NURBS topology, and then eventually I will upload organize more webinars. So thank you very much, and see you soon. Bye, guys.